We got another one, kids. So it was about a year and a half ago that Facebook, I mean Meta, they actually had some research. This happens once in a while, and it was called a large concept model. And a large concept model is where you're still mapping into a vector space, what's called the latent space, which is inside the neural network's brain. It's mapping every input as a line, a vector pointed in some direction, some distance. So it still vectorizes all the inputs into a latent space. This is different from a knowledge graph. Lots of people got excited about knowledge graphs. They have a few areas where they're useful, but there's a big problem with knowledge graphs. Knowledge graphs are just like pins on a cork board. You know, the meme of the guy's like, oh, I figured it out. And it's got all the yarn connecting the pins on the board. Knowledge graphs are a graph theorist's kind of graph where it doesn't matter what the coordinates are. There are no coordinates. It's just about the connections between each node. Each point has a connection to other nodes. And you can move the pins on the board anywhere you want as long as the connections stay the same. So it's not dimensionalized. That helps for some scenarios, but it introduces a big limitation that Cartesian vectorized latent spaces don't have, which is that there's no distance metric. You can't measure the distance between points in a knowledge graph. But when you have a latent space that's using vectors, you can measure the distance between two vectors, and it also gives you a directionality. So in the latent space of language models, large language models, for example, there's two vectors for man and woman, and two vectors for king and queen. And if you look at the vector between man and woman, it's the same direction and length as the vector between king and queen. Stuff like that. So a latent space that's dimensionalized, like a large concept model, has certain benefits. And what Meta was doing with the large concept model is they would take a statement and feed it in and then see if they could spit out the same idea using different words. That's where you want to hit. That's the direction you want to be going in neural network research. Large concept models are going to win. So the essay you can look up with details on all this, just search my name in the title. It's Next AI, Large Concept Models. There's also one called Large Concept Models Will Win. So the thing that I'm adding, there's a couple other wrinkles, but one of the main concepts is when you take a sentence that has a concept in it and you project it into this latent space as a vector, you're going to be translating it back into a new sentence that says the same idea using different words. That's what Meta did. But then you want to take that new sentence, saving the same idea with different words, and put it back in the latent space, and then translate it again, and then translate the translation. Translate. We've all done this with Google Translate, where you just keep translating a translation of translation, and it drifts. It turns into something totally different. So what you're going to see as you translate the translation of the translation is that vector in the latent space starts to move. And that drift of the latent space vector tells you that that concept is not solid yet. So that the drift in the latent space vector is your reward function. That's the key idea about where to go with large concept models. As the translation drifts, that drift is your signal that you're going to feed in. That's your reward function. And now to go a bit deeper, you want to build up to higher order concepts in layers of smaller concepts. And you want to build up organically. So whenever there's ambiguity, two different statements lead to the same vector, now you know that there's more to do. And as you move up in layers of latent space vectors, layers of concepts, what you're going to be building up is a sparse representation. So you can look up Jeff Hawkins' company Numenta. They use sparse distributed representations. I like where they're coming from. Jeff Hawkins was the guy behind the precursor to the smartphone. And he wrote a book in 2006 called On Intelligence, which is great. It talks about how the 6-layer stack in your prefrontal cortex is the first layers are dealing with trying to predict what's going to happen next. And when they're wrong, that's what sends a signal to the next layer. And the next layer tries to predict when the layer beneath it is going to be wrong. And then the layer above that tries to predict when the layer beneath it is going to be wrong. And so you got these layers of error correction. And that's what allows you to build up complex abstract concepts. So the large concept model essays, they talk about the details of how to work large concept models to organically build up sets of abstractions into very high order abstractions. And now a very large complex concept can be represented as a sparse distributed representation of those latent space vectors. There you go.